Spenta Wadia is the Infosys Homi Bhabha Chair Professor and Founding Director of the International Center for Theoretical Sciences, ICTS, TIFR, of the Tata Institute of Fundamental Research. ICTS is a unique institution involved in furthering the boundaries of fundamental research and science education, emphasizing that science is one story. He has made basic contributions to quantum field theory, statistical mechanics, string theory, and black hole physics. His other interests are in complex systems and cross-disciplinary biology. He is an alumnus of St. Xavier's College, Mumbai, Indian Institute of Technology, Kanpur, City University of New York, and the University of Chicago. He has held long-term visiting positions at the Institute for Advanced Study at Princeton and CERN, Geneva. His recognitions include the TIFR Alumni Association Excellence Award in 2016, the World Academy of Science Physics Prize in 2004, the Physics Prize in Abdus Salam International Center for Theoretical Physics in 1995. He's a distinguished alumnus of St. Xavier's College, Mumbai, and a member of the Indian National Science Academy, the Indian Academy of Sciences, and of TWAS. He was recently elected as International Honorary Member of the American Academy of Arts and Sciences, AAA and S. Professor.
Thank you very much for inviting me to this program on Space Day. Thanks to Jaya Nair for reaching out, and my apologies for not having joined you in person, simply because I'm in the middle of another meeting at the ICTS. Okay, so I thought I'll talk about time instead of space, and ultimately we'll see that it all mixes up. So in the background, you see the photograph of the ICTS campus, and with that, let me begin. All right, so I'll basically talk about the history of time, briefly. And so, it sounds very similar to the title of Stephen Hawking's famous book, A Brief History of Time, but I couldn't find a better title to name what I'm going to talk about. So our awareness of day and night is obvious as the sun appears and disappears daily. And this is related to the spinning of the earth on its axis, an explanation that came much later. But the awareness of some sort of an idea of the passing of time is from antiquity, related to the rising and the setting of the sun. It's also true, because we have evolved on Earth, that day and night are wired into our genes. There is a secretion of melatonin in the evening that induces sleep. Such circadian rhythms are present in animals, plants, and other living matter also. Just the awareness of the duration of a year, for example, during the early history of our species, is through the seasons and their manifestation in terms of hot and cold weather, the appearance of fruits and flowers, migratory patterns of birds and animals, and when agriculture came about, a time for sowing seeds and a time for harvest. I've just made some pictures here about the reason, which of course we realized much later, as to why we have seasons. It has a lot to do with this amazing inclination of our planet in the plane of its orbit by approximately 23 degrees. And just to sort of invite your curiosity, if this angle were a bit different, I think the history of the Earth would be very different. Just think about that, and perhaps it's a very interesting point about this tilt being so precise that brought us all about here. Okay. So there is another celestial phenomena which, people observed long ago. Since the beginning of time, that the waxing and waning of the phases of the moon and the rise and ebb of tides, which is caused by the moon's gravity. And due to the synchronous rotation of the moon on its axis and the orbit around the Earth, so it became a natural timekeeper. Okay, So a lunar month became a natural unit of measuring time between identical phases of the moon. So early in history, it was our sensory perception of the motion of the Earth in the solar system and the visible periodicity of the phases of the moon that gave us some understanding or led to a notion of this. It's a very abstract concept of the passing of time. So the notion of time, in some sense, grew out of the almost periodic cycles of the natural world. And that fact has continued into the modern world and perhaps grew out of the necessity to organize our lives and also to understand the natural world around us, as I will sort of indicate as we go along. So more sophisticated timekeeping devices emerged based on astronomy. One imperative came from navigation at sea. As the seasons change, the movement of constellations, that is, the groups of stars, is visible in the night sky. And this is due to the orbit of the Earth around the sun. So here is a very nice quote from a book, which is very informative about these ideas, that the synchronization of celestial and terrestrial changes naturally suggest a causal relationship between them. And so observing the motion of constellations and planets became a way of explaining and predicting events on Earth. However, celestial timekeeping has inaccuracies built into it because celestial motions are never perfectly periodic. This is a very important point, why they are not perfectly periodic. And I leave the discussion of this to future, I mean, amongst you people, but let me just proceed now. For example, the length of the day measured between equinoxes, okay, is 365.2422, which over centuries, say, let's say 5 centuries, can grow to a very large difference of 121 days. And similarly, the average length of a lunar month is 29 days, 12 hours, 44 minutes, and 2.8 seconds. It's the accuracy of this is not important for the concept I'm trying to put forward, actually. So now happens a very important shift. Up till now, time was being perceived, the way we sort of organize and order events, societal events, or even the understanding of, where and how and when the world around us through our sensory perceptions was done in terms of celestial objects, okay? So societies then started developing terrestrial timekeeping devices, and I have a few photographs here, like the water clock, the sundial, sand glass, and incense clock. And these devices are not very accurate timekeepers. You can see, for example, in the picture, the marine sand glass. And, it is related to the hourglass nowadays, often used symbolically to represent the concept of time. There is the ancient Egyptian sundial, the limestone Egyptian water clock, and so on. The very interesting one is an incense clock. Time was measured by the means of powdered incense burnt along a pre-measured path. So somehow, in some sense, length translates into time in such a device. And these devices are not very accurate. For example, a water clock's measure of time obviously depends upon the temperature of water. So in a very cold climate, it works differently than in a very warm climate. Okay. But the whole point I'm trying to make is that there is a sort of a desire, or in people all over the world, actually, it's not only in one part or the other, to try to make a device that will, record time in some sense. I don't have the words, actually, because something very abstract about this whole thing, really. Okay, now comes the big breakthrough. So the oscillator and escapement mechanism that creates the regular periodic beat of timekeeping was originally developed in countries like China and the Middle East. And towards the end of the 13th century, European craftsmen, as I really emphasize this word craftsmen, refined this mechanism to create the first mechanical escapement mechanism, okay, that led to the mechanical clock. And you will see, for example, large mechanical clocks in many, many cities of Europe. And the one I have pictured over here in Rouen, I have myself seen actually. It organizes life of the society in that town. In antiquity, if you go back, actually. All right. So the mechanical clock propelled a new conception of time into public consciousness, transforming it from a constant flow embodied in steady emissions of water, sand, mercury, to a quantified count, divisible, discrete, and measurable. And as with monastic bells, public clocks organize citizens into a cohesive unit, turning what had previously been private lives into communal tides that rose, worked, and retired as one. So the clock is not merely a means of keeping track of the hours, but of synchronizing the lives of men. I think this is a very nice set of quotes from this book by James Vincent, which I thought I'd mention to you. Then finally, the pendulum clock was conceived by Galileo, and the first working model was crafted by Huygens, and it was constructed by Coster in 1656. Okay. All right, all this is great. So we are somewhere in the middle of the 17th century. So what is the impact of this? This is the point I wanted to get to in this talk. Besides all the physics I'll tell you later, that the clock, which is a machine, became a symbol of a new way of conceiving the universe, mechanical philosophy. The mechanical philosophers reasoned that if clockwork was able to capture the movement of the stars and bring an elaborate automata to life, who was to say that the natural world did not operate under a similar logic? If nature worked like a machine, then it must rely on observable cause and effect. I think it's a very profound statement, actually, that in some sense, in a very deep sense, from trying to understand time in terms of celestial objects and their motions, there was an object that was constructed by craftsmen and scientists and engineers on Earth. And I think that made a very profound impact on the fact that our lives need not be necessarily dictated from the heavens. And Galileo Galilei, more than any of his contemporaries, crystallized the integration of experiment and theory and laid the foundation of the scientific method. So this is the first part of my talk, which I've ended now. And the main message is that in some sense, in order to capture experimentally or in a practical way the notion of time, humankind was led to the invention of the terrestrial clocks, and the mechanical clock actually, in some sense, in some very deep sense, is the precursor of the scientific revolution. Okay, all right. So when the year Galileo passed away, 1642, his successor Isaac Newton was born. Okay, so now I come to the second part of my talk, and this is a physics talk from now on. Up till now, it was about history. Okay, so okay, before I do that, let me just jump centuries ahead and say something about clocks. The mechanical clock that worked on the laws of classical physics was a standard timekeeper well into the 20th century, till it was replaced by devices that work on quantum mechanics. So I'm not going to tell you what quantum mechanics is. This is next year is the 100th anniversary, but it's a new formulation of the laws of nature, what we believe are the true laws of nature. So for example, based on those principles, the crystal quartz, the quartz watch everybody wears is piezoelectric. And, there's a precise oscillation that is then sort of translated into the mechanical motion of a hand on your clock dial. But the most accurate timekeeper is the atomic clock. And there also we are talking about periodicity, but periodicity in a quantum mechanical sense. And the most accurate clock is devised in terms of the transition levels of the cesium-133 atom. I just had to say this because what I want to say is that our methods of timekeeping also reflect the revolutions of science, that the mechanical clock was based on classical physics. These atomic clocks and the quartz clock is based on the principles of quantum mechanics. Okay, now, so after this, I want to start on the Newtonian framework of physics. So you might think this is all very trivial talk, but it's not. I'll try to sort of clarify what seems obvious was perhaps not obvious in the 17th century. All right. So this is Isaac Newton and his Principia Mathematica, which appeared in 1687, laid the foundation of the mathematical foundation of the scientific method in some very deep sense. So Galileo and Newton. So he establishes a framework of mechanics that all natural processes take place in space and time. So this seems very trivial statement, but it's not. I think to realize this type of abstraction is truly profound in my opinion, actually. So Newton formulated the laws of motion in terms of the flow of time of a point particle in 3 dimensions. So he took the Cartesian idea of indicating a point in space by 3 numbers and saw how that point moves along a certain parameter, which you call time. So what that time has to do with the time we have been talking about before is the connection between experiment and theory. So I've just briefly mentioned to you what you learn in your first course on mechanics. You have a curve in space and velocities and accelerations are defined in terms of mathematics or calculus. But there's one important point here in this slide is that time is absolute and the same for all observers. Coordinates may be rotated or moved with constant velocity. You traveling in a train, somebody in an airplane, me sitting here, all our clocks are synchronized. And I think this is the foundation of Newton's theory. So anyway, there is some, once you have a framework, you talk about laws, force laws, and how things are sort of governed by them. So this is the famous law of gravitation. You may wonder why I'm talking about gravity actually in this talk of time, but you will see later on when we talk of general relativity that the notion of gravity impacts our understanding of the notion of time. So the gravitational force is instantaneous. This is something which Newton was very uncomfortable with, but his main point was that if you do this, if you write these equations, then you can sort of make a prediction about the elliptical orbits of planets around the sun. Okay, so this is just one slide on Newton's law of gravity, and this gravitational law is universal. It applies to any 2 objects with masses m1 and m2. Okay, all right. So, just because this is a IIIT talk, I just wanted to emphasize that we usually talk about Kepler discovering the planetary laws in terms of ellipses. The Earth moves in an ellipse around the sun, but how did he get to that? So he looked at astronomical observations, especially by his predecessor, Tycho Brahe, and it took him approximately more than 20 years to figure out that there was a symmetry in that data. There was big data and there's a symmetry there. And the symmetry was to change the center of the analysis from Earth to the sun, having this Copernican idea in mind. And once you discovered a symmetry, all those data fell into elliptic orbits. Actually, I just wanted to say that this Kepler actually maybe the first data scientist who found a symmetry in big data. Okay, actually that's true. What I said is true. All right, now this is about mechanics and Newton, and as time goes on, scientists discover the laws of electricity, magnetism, electromagnetic waves, and also something about the speed of light, which I will just very briefly talk about. Okay, so we come to Faraday and Maxwell. So Faraday demonstrated that light is polarized by a magnetic field. So there must be some deep connection between optics and electromagnetism because of this. And so Maxwell unified electricity, magnetism. I mean, this is one of the most amazing works in the history of science. Predicted the existence of electromagnetic waves and identified light also as an electromagnetic wave of oscillating electric and magnetic fields, exactly like in this simple picture over here in the middle of the 19th century, okay? And one very important, extremely important thing that emerged from Maxwell's theory was that charged particles don't interact instantaneously. And the force between them is transmitted by the electromagnetic field at the speed of light, which is finite. Okay, so these were equations. Some things were predicted, but as time went on, and this is the point which I always want to emphasize, that Maxwell's theory was experimentally confirmed. That's why it's the truth. And by Hertz, by his discovery of radio waves, and by Rangan, by his discovery of X-rays. So we have Maxwell's theory, prediction of electromagnetic waves, and the constancy of the speed of light. Now, once you realize that there is something about the constancy of the speed of light, that Maxwell's equations somehow implied something like that, not very directly, I mean, not at that time, but later on in history. Einstein saw a very, very deep, what shall I say? It's a, a very revolutionary point of view here, that he saw that the constancy of the speed of light implied by the structure of the equations of electromagnetism can be sort of put in a very simple form, in the sense that if you have two observers actually, or two frames, somebody running at me at a certain speed, emitting, with a torch and emitting some light, and the speed of light for me and for that observer would be the same. It's very counterintuitive, but this is the deep point, that it is the same. And if you accept it, and this is experimentally tested later on, you arrive at the laws of special relativity. Okay, and here I have a little sort of a cartoon of how the constancy of the speed of light changes our notion of time, that simultaneity for one observer is not necessarily simultaneity for the other one. Okay, so I leave you to work this out. I don't think, perhaps I don't have the time to really explain to you this, but let me just say that you'll see that this there's a spaceship, there's a astronaut there, and he has lasers bouncing between two mirrors. Okay, so just up and down. That's what he is doing. So he can measure time by looking at how many times the laser has bounced between the two mirrors. But for an observer who is stationary with respect to this spaceship, since the speed of light is finite, the path of light is elongated, okay, as you see in the next figure. And then it's not a very big deal using just the triangle theorem to work out that the time differences for the observer at rest and the time differences for the observer who is the astronaut is given by this very simple formula, actually. Okay, it's very easy to derive this formula, but this is the essence of special relativity. And it follows from that one principle that the speed of light is the same for all inertial observers, means observers who are moving with respect to each other at a constant speed. Okay, and the speed here is v. So this is one slide on the theory of special relativity. All right. Okay, so now comes the next important step, actually, that perhaps why I felt that on Space Day I can also talk about time is because they get mixed up. So we come to Hermann Minkowski, who realized that space and time form a certain geometry, very much like Euclidean geometry, okay? And in Euclidean geometry, for example, if you look at small distances between points, then they can be written in terms of the square of the distance in one direction plus the square of the distance in another direction, etc. Okay, Minkowski realized that if you change the sign in front of the time, then you can derive all the laws of special relativity using a geometrical idea. And so he introduced the notion of geometry in special relativity, okay? So we had the constancy of the speed of light that led to space and time adjusting themselves in some way in order to maintain the constancy of the speed of light. And here now, the next big step is the geometrization of space-time by Hermann Minkowski, who was one of Einstein's teachers, incidentally. All right, so now we turn to the next chapter. How the notion of time is impacted, or how our understanding of time impacts physical laws, okay? So here are a couple of slides to explain to you the general theory of relativity, okay? So we are something around 1908 now, 1908, yes, 1905 approximately, when Einstein starts worrying about the fact that if the speed of light is the same for all observers in relative motion, there can be no action at a distance. Just like in electromagnetic field, the interaction is not simultaneous. So there must be something wrong with Newton's law of gravitation, and it has to be modified. So this is the problem. Now, I really encourage you to read about this history because it's one of the great struggles of modern scientific history, that between 1905 and 1915 approximately, Einstein completed the general theory of relativity, which is a theory of gravity in which the force of gravity is not instantaneous. And it is communicated at a finite speed c, the same as the speed of light, by changes in the geometry of space-time. So there doesn't seem to be once Minkowski realized the geometrization of, space-time or special relativity, to arrive at this is a long way, is a long uphill, but he was able to do it. It's a great history. I don't have much time to go into it. And I invite you to read Abraham Pais's very famous biography of Albert Einstein. Actually, it lays it out very nicely. So here, for example, in the interaction of masses, the role of the electromagnetic field is played by the waves of the metric of space-time. And the force of gravity is not instantaneous, as I mentioned. And it's very much like mimicking the electromagnetic field, but in some geometric way. So anyway, these are some of the reasons which Einstein was worrying about for many years, and ultimately, I'll tell you what the theory is pictorially, and let me just move on from here. So let me just describe to you what this general theory of relativity is. So general theory of relativity describes the changes of the geometry of space-time caused by massive objects to which other objects respond. Okay, so John Wheeler famously said that matter tells space-time how to curve, and curved space-time tells matter how to move. So now space-time is like an elastic grid, you know. So if you have a very heavy object, it distorts space-time, and then somehow the lighter objects move in that distortion. It's very much like if you have a trampoline and you put a heavy ball on it, you can set the smaller balls in motion around it. Okay. Now that's just a cartoon, but so here is a animation of this simple idea of space-time as an elastic grid. But you might wonder actually that if it is an elastic grid, why is it that we are not noticing it in our daily lives? I mean, when I shake my hand, you don't feel a gravitational wave, right? And this is because, this grid is extremely stiff, and it is approximately 10 to the 20 times stiffer than steel. So this grid that we are talking about of space-time, elastic grid, is extremely stiff. And this is why in your daily life or in most phenomena, we don't sort of observe it. And it takes very strong and cataclysmic interactions like the merger of two black holes to give rise to gravitational waves, or jiggles on this fabric of space-time, okay, which these gravitational waves were first observed in 2015. Okay. So anyway, now there's a very important point here I want to make, that Einstein's theory implies that time flows differently for two observers in a gravitational field. Now let's see if this, so you have two observers, one on a lower floor and one on an upper floor, okay? And see, you see this animation is due to a very good friend of mine, Juan Malasena. So I have permission to use it. So this says that the time flows slower, okay, on the first floor than on the, let's say, the 20th floor. You can see that it moves faster. So the more you're away from Earth's gravity, time flows faster and faster. Of course, you don't notice it because, for a height of 100 meters, the change is 1 part in 10 to the 15. You see, this is the point. So that's why we don't notice it, but it's there. And it makes a difference if the height is, let's say, about maybe 20,000 kilometers or something like that, or the place where all these satellites are moving that communicate with us. And this effect is very important to take into account for the accuracy of the global positioning system. I just want to tell you that these very deep ideas, abstract type of ideas of general relativity are used in practical daily life, actually. Okay, so that's about the GPS. This is another demonstration of the same idea that if you have a star, and as you go towards the gravity of the star, time keeps on slowing down. Precisely this by this factor, which I have just written on the top, actually. Okay, so this is just to give you an idea that if you're very far away from a huge object, time flows faster than near that object. And in fact, if you have a black hole, and this is one way of defining a black hole, time just stops at what is called the horizon of the black hole. So just since there was a talk about Professor Vishweshwara, I just wanted to mention that one of his great scientific contributions was to understand what happens if you throw some matter in a black hole, and what type of waves are generated, and these are called quasi-normal modes. So he called himself a quasimodo also at some point. Anyway, I just thought I'd mention this point to you about his contribution over here. It's a very fundamental contribution to general relativity. Okay. Now, in some sense, I'm the main part of my talk is done, in the sense that I began with the celestial ideas about time, how human beings had the need. This is all very need-based, to organize life, to go hunting, come back, have food, and how the celestial sort of instruments of time were replaced by instruments of time on Earth, which were made by craftsmen and engineers, and how that led to the idea of the mechanical clock, and which raised so many questions in natural philosophy and was a precursor of the scientific method. It was, in a sense, summarized. A lot of thoughts are summarized by some people, by Galileo, and then led to the Newtonian framework for understanding the laws of nature in terms of an absolute time, and how discoveries in physics actually led to a change of that idea, especially the discovery of the laws of electromagnetism by Maxwell led to a revolution in our notions of space-time, because then space and time were getting mixed up because of that. Time is not absolute anymore. And then how Einstein, from there, came up with the general theory of relativity in terms of geometry, and how that type of viewpoint predicts its influence on our notion of time, that how time sort of slows down as you go away from gravitating objects. So in a sense, our ideas of time are impacted by our progress in the laws of nature, and progress in the laws of nature. Its most important impact on our notion of time is the fact that the most accurate clock today works on the laws of quantum mechanics. I couldn't elaborate on it because of the shortage of time. But now let me end this talk with something else, which is also connected to a certain notion of time, which we are all familiar with, actually. Okay. So until now, we discussed the emergence of the concept of time and its measurement in terms of regularities observed in nature. The motion of the Earth in the solar system, the passage of constellations in the sky, water clock, sand glass, mechanical clock, quartz clock, and the cesium standard. Okay, this is what we did. However, most phenomena in the real world exhibit a fundamental irreversibility. For example, consider the burning of a piece of wood. The final state is simply ash and carbon dioxide and other gases. So one never observes this final state assembling itself back into a piece of wood, right? So from a thermodynamic point of view, one would explain this by saying that the entropy of the final state is greater than that of the initial state of wood, and hence, by the empirical second law of thermodynamics, the time reverse process does not happen. And to quantitatively understand this phenomena, Ludwig Boltzmann in 1866 introduced a formula for the entropy of a gas as a measure of the number of internal states that make up the system, and showed under reasonable hypotheses that the randomness of the collisions, that the entropy always increases in time. This is the famous H theorem of Boltzmann. And this laid the foundations of what we today call the whole area of statistical physics, how you make statistical statements about large systems. So it was subsequently adopted in quantum mechanics by John von Neumann 1932, and there is a whole meeting going on at the ICTS, more or less discussing the contribution of John von Neumann to quantum information. And it was also taken up by Claude Shannon in 1948, who gave a discrete version of Boltzmann's formula. And that formula, the Shannon entropy, forms the foundation of information and communication theory. I just thought sort of the scientific part of this talk should end with Boltzmann, von Neumann, and Claude Shannon also. Okay, so the last science slide is about, this is it. This is the history of the cartoon of the history of the universe, you see. We know quite a bit about this flow of time over here till we come to a very cold universe in which human beings are there and complex systems are formed. But much of the important research today is in trying to understand this cartoon in its details, and also the cartoon towards the left side, we almost beginning the Big Bang, we have very little understanding of actually. And many of us who work in an area called string theory and quantum gravity are interested in the beginning of time. We don't know what that is really, actually, especially when, you know, the grid of space-time is very, very, very hot and fluctuating. We don't know that. But this is just it's an amazing picture that encapsulates history in time of our universe. Okay, so let me just end with this quotation from Brian Swim. So I first saw this in the Israel Museum in Jerusalem, and I was just very struck by it. So I have adapted it for this talk. There are other things there written which I do not agree with, so I've removed them. So most amazing is this realization that everything that exists in the universe came from a common origin. The material of your body and the material of my body are intrinsically related because they emerged from and are caught up in a single energetic event. He's referring to the Big Bang. Our ancestry stretches back through the life forms and into the stars, back to the beginnings of the universe. And all this is new. None of the great figures of human history were aware of this. We are the first generation to live with an empirical view of the origin of the universe. We are the first humans to look into the night sky and see the birth of stars, the birth of galaxies, the birth of the cosmos as a whole. Our future as a species will be forged within this new story. So, here we are after approximately 13.7 billion years in this vast, cool universe on a small rock called Earth of age 4 billion years, sailing through the universe as part of our galaxy of the Milky Way. The Milky Way has approximately 100 billion other stars going around. And this immensity and complexity must make us all feel humble. This is the point I want to make in this talk, that let's feel very humble in this. You know, the fact that you know all this must make you feel humble. And we just have understood just a tip of things, actually. There's much more to be said about the perturbation of the state of the earth by us. The state of the earth is perturbed by us humans pretty badly, I think, and about the preservation of our species and others that we coexist with. So one of the most important developments of the last millennium is the scientific method as a means to access the idea of the truth. And I think in the previous talk also, Madhusudana mentioned all these things in connection with mythologies and stuff like that. It's very important to how to access what is true. And there's a method that has emerged in the last millennium. It's called the scientific method. And hopefully you will imbibe this and see the world in all its aspects, including our history, our sociology, our environment, and our survival as a planet through this lens. Thank you for listening.
Sir, we have a few questions here. I'll hand over the mic.
Yeah. Stop.
Hello. Thank you, sir, for the talk.
Hi. Yeah.
So my question is regarding the arrow of time. So we think it relates to
Right.
principle of irreversibility, increase in entropy. So any
Yeah.
cases where we find instances of Maxwell demons, like say in non-equilibrium systems and granular matter, there has been cases where
Mm.
people have hypothesized Maxwell demons. So
Yes.
does that violate the idea that the arrow of time goes in one direction? I mean, what is your opinion on relating these two
No,
concepts?
I think, yeah, I think you can have systems in which, the laws of nature are time reversal invariant, the laws we work with. I mean, okay. And now, if you have large systems obeying these reversible laws, the whole idea is how is it possible actually for a system obeying the laws which are reversible to have irreversible behavior? Okay, so this is what the whole subject of statistical physics deals with, and the idea of entropy, etc., etc. What you are talking about is a local fluctuation there, and yes, that can be possible. I can imagine that in a very big system also some states can be reversed, but by and large there is very low probability for that. So by and large, the second law of thermodynamics really holds for large systems. Does that answer your question?
Yes, sir. Thank you.
Sir, good afternoon.
Yes.
So the question is, sir, what would be the strength of this space time continuum at in the beginning of the Big Bang when it was hot and fluctuating? You said that the current value could be about like 10 to the power 20 times that of the steel. So we don't. It's very difficult to say feel that particular bent or anything. But what could
Yes.
be in the beginning of the universe?
Yeah, you see, so that's the problem actually. So I think we don't have so when we talk of beginning, I mean, we are talking about something like Planck time or, around even before inflation, which is on this cartoon, you can see that is even before 10 to the minus 36 seconds, more or less our description of the world in terms of classical gravity is okay. And I was referring to this grid of classical gravity, okay? Now, when gravity becomes quantum, I absolutely have no idea of how to pose this question, how to pose a question there also. I don't know. We are trying to understand these questions in terms of uh, a more basic theory of gravity called string theory. But I cannot answer this question. No, I don't know. That's the answer. Because I don't know whether space and time that we know it today, that type of concept was there before. We don't know that.
Thank you, sir.
Yep.
So, Professor Spenta, thank you so much for this wonderful talk. I think we got a good dose of physics with this talk, and this has been great. Yeah, thank you so much.
Okay.
Yeah, thank
All
you for
right.
joining us.
Have a good day.
Yeah, you
Bye-bye.
too.
Ciao.
Bye.